This video we're going to continue talking about the electronic structure of the atom. So we're going to start first with a unique property of electrons that was discovered through the experiment that's shown here on this slide. So this experiment is sometimes called the Stern-Gerlach experiment. And what this experiment did is they took a source of, and in this picture it's hydrogen atoms. In the actual first experiment that was done, these were actually silver atoms, but the point is the same. So what we're doing is emitting a source of hydrogen atoms, and they're flying and hitting the screen, and there's a tiny hole that allows some of the atoms to bleed through in a narrow beam into this low pressure chamber. Then inside this low pressure chamber there's an inhomogeneous magnetic field, so a non-uniform magnetic field. So here's the north magnetic pole and the south magnetic pole, and it kind of has this funny shape. And what was discovered is when you pass this beam of hydrogen atoms through, they get deflected in one of two places, and only two places. So you get a spot up here at the top, and you get a spot down here at the bottom. And so there's no smearing out here in between. So just two spots. So that's a very interesting phenomenon. So one way that one could explain this phenomenon is to imagine that the electron was like a little tiny ball of electric charge. So we think of, in the quantum mechanical world, as electrons being a tiny point particle. But let's imagine, oh, that's a terrible looking ball. So let's imagine that it's a little sphere, right? So that's still a terrible looking sphere. So it's a little sphere. But electrons we know have negative charge. So I'm going to draw a little minus sign in there. And so this is now a little ball of charge. Now we're going to imagine that this little ball of charge is rotating. So it's spinning around its axis. So just imagine that you put a stick in the middle and you let the electron spin around this axis. So as it spins, the electron is going to generate a little magnetic field. Just like electrons flowing through a wire will generate a magnetic field. That's how we make electromagnets. And that magnetic field is going to cause the electron to act in a particular way when it flies through this magnetic field and be deflected in one direction. If the electron were spinning the opposite direction, then it would cause it to be deflected in this other direction. So apparently electrons have this special magnetic property that is associated with something that we call the spin on the electron. Now this model of the electron as a ball of charge that is just spinning is just that. It's just a model that we use to explain this behavior. So there's no actual evidence that electrons are actually spinning on their axis like this. Anyway, so this is our model. So here are two pictures of the electron. In this case, the electron is spinning around counterclockwise, and as it does so, it generates a magnetic field with, say, the north magnetic pole pointing down and the south magnetic pole pointing up. And we call this particular spin, spin up. And we give it a quantum number. So there's a quantum number associated with this particular behavior of the electron. And that quantum number is called the m sub s quantum number, or the magnetic spin quantum number. And so in this case, when we're talking about an electron that is spin up, we're going to call that plus 1/2. So plus 1/2 is spin up. Spin up. So over here, this is spin down. So the electron is now spinning, we imagine in our model, in the opposite direction, in the clockwise direction. And we're going to call that spin down. Oftentimes we will represent spin up electrons by a little arrow pointing up, or maybe even a half arrow like this. So I've only drawn one side of the arrow. Similarly, spin down is an arrow pointing down, or perhaps a half arrow pointing down. So that's how we're going to represent the electron, and it will have these two possible values of m sub s, plus 1/2 for up and minus 1/2 for down. So you don't need to remember the directions that these little models are spinning. That's just to show you a picture at a spinning ball of charge. Gives you a little magnetic property. And it turns out that spin is important. Both the spin of electrons and the spin of the particles in the nuclei give rise to the magnetic properties that we observe in materials in nature. So the reasons that magnets are magnets has to do with the electrons and the nuclei and the spins on those particles. Now, there's a very important property of spin that was then discovered by looking at experimental data. So I should point out that Schrödinger's equation does not predict spin. The Stern-Gerlach experiment proved that demonstrated that it existed, and then we had to go into our Schrödinger equation and add spin back into it by putting in some rules. And one of those rules is this thing called the Pauli exclusion principle. And we're going to get to that in a little bit more detail in a minute. So now let's think about electron spin, and now we're going to think about something more complicated than the hydrogen atom that we used the Schrödinger equation to solve for. So we're going to look at multi-electron atoms and something that's called the orbital approximation. So why do we have to use an approximation? Well, it turns out that the mathematics of the Schrödinger equation is impossible to solve exactly. Now, it's not that it's just really hard. We can actually prove that you can't solve that equation. But what we can do is solve it approximately. We can get numerical approximations that get better and better and better depending on making better and better approximations and doing our calculations to finer and finer precision. So the way this approximation works, this orbital approximation, is we're going to assign each electron in an atom to a hydrogen-like orbital. So we've already talked about the hydrogen-like orbitals, the 1s, the 2s, then there's the 2px, the 2py, the 2pz, and so on. So what we're going to do is imagine that something like that exists in all atoms, and we're going to assign all of the electrons in any particular atom to one of those orbitals. Then the approximate solution to Schrödinger's equation is going to be taken as the product of all those orbital functions. So remember, orbitals are mathematical functions that describe a region in space where it is likely to find a particular electron. So the solution to the Schrödinger equation will then be the product of all those orbitals. We'll just multiply those mathematical functions together, and that'll tell us something about the whole atom. So another important consequence of making this orbital approximation is that the energies of the orbitals, what we call, split and shift. So the 4s and the 4p, for example, will no longer be at the same energy like they are in the hydrogen atom. The 4s actually goes down in energy, and the 4p's go up in energy. So that's what we mean by splitting and shifting. So those energies are going to move around. Why do they move around? Well, it all has to do with the interactions between the electrons in multi-electron atoms. So what we're going to be interested in is figuring out the ground state, which is the lowest energy electronic structure of the atom. And in order to use this orbital approximation, we are going to follow 3 rules. And those 3 rules have the following 3 names. There is the Aufbau Principle, the Pauli Exclusion Principle, and Hun's Rule. So let's look at each of those in turn. So first we're going to start with the Aufbau Principle. So this is what I was talking about the shifting and splitting of orbital energies. So this is an energy level diagram, and it shows that, for example, the 2s orbital is lower in energy than the 2p orbital. And you'll see that this listing of orbitals gives us the typical filling pattern that we use, that we figured out from photoelectron spectroscopy. So the 1s is first, then the 2s, then the 2p, the 3s, the 3p, the 4s, and then the 3d. The other thing that you can notice by looking at this energy level diagram is up here at high energies, a lot of these energies are very close together. And in fact, as we start adding electrons to the various orbitals, some of these energies will actually move around due to shielding and screening effects. So the Aufbau Principle says to get the lowest energy, what we call the ground state, orbital electron configuration, what we're going to do is fill the orbitals from low energy to high energy. So this diagram is another energy level diagram, so energy is increasing along the y-axis here. And then we've divided these up into the various shells and subshells. So the n=1 shell has only one subshell, the s subshell. The n=2 subshell right here has 2 subshells, an s and a p, and so on. The n=3 with an spd, n=4 with spdf, and so on. And then I've lined them up according to their energies. So we're going to start assigning electrons, all of the electrons that an atom has, at lowest energy. So we're going to start putting them here and work our way up. So 1s first, then 2s, then 2p, then 3s, then 3p. Now you might think we would do 3d next because we're working on the n=3 shell, but we see, aha, this 4s is lower in energy than the 3ds. So we're going to start filling that one next. So we're going to go to the 4s, then the 3ds, then the 4 p's, and so on. So it works out kind of like that. Our second rule is something called the Pauli Principle, or the Pauli exclusion principle. And it's stated this way, that no two electrons in an atom can have the same set of 4 quantum numbers. So remember, there are 3 quantum numbers associated with an orbital, n, l, and m sub l, the principal, angular momentum, the magnetic quantum number. And now we've got this new one, the magnetic spin quantum number. Okay, so this is the one right here, this last one, m sub s, that can be positive 1/2 or negative 1/2. And again, that just characterizes what kind of spin we have on our electron, whether it's spinning clockwise or counterclockwise, and what kind of magnetic property it will have, whether it would be deflected upwards or downwards when we pass it through that non-uniform magnetic field. So as a consequence of this principle that you can't have 2 electrons with the same set of 4 quantum numbers, is that only 2 electrons with what we call paired spins can be assigned to each orbital. Paired spins means opposite. So we have one spin represented by this up arrow that's up, plus 1/2, and one spin that's down, minus 1/2. Once we've got one of each, one up and one down, we can't put another electron into that same orbital represented by this little horizontal line here, because it will have the same set of 4 quantum numbers as another electron. And Pauli said we can't do that. So where does the Pauli principle come from, by the way, and where does the Aufbau principle come from? It comes from looking at experiments and getting quantum mechanics to agree with experiments. Now later we've been able to take quantum theory and add in some other theories that allows us to effectively show where the Pauli principle comes from. So we've been able to prove it from a theoretical point of view, but originally it came from experiment. Finally, our third rule is Hund's rule. So Hund said that the lowest energy state of an atom has the greatest number of parallel electron spins. So what does parallel electron spin mean? It means that they are all in the same direction. So the electrons are all spinning in the same way to give, say, up arrows, or all down arrows. So the more of those that you can have, the better. So when we have unpaired spins, so that's an electron in an orbital by itself without a corresponding partner pointing down, for example, that produces what we call a paramagnetic atom. A paramagnetic atom will be deflected by one of those non-uniform magnetic fields, and those atoms can have magnetic properties. So atoms are what we call diamagnetic if all spins are paired up. If that is the case, and you were to shoot one of those atoms through a Stern-Gerlach experiment, through one of those non-uniform magnetic fields, the atom would pass straight through without being deflected. So if we have an up arrow for every down arrow, we say it's diamagnetic. If we have an imbalance, so one more up arrow than down arrow, we're going to have a paramagnetic atom. So now let's do an example. So let's apply the orbital approximation to an oxygen atom. So the way we're going to do this is to first draw this energy level diagram. So I'm going to draw an axis right here, we'll label it energy, and then I'm going to start down here with some little horizontal lines that represent the different orbitals. So here's a 1s orbital, so this little line represents the energy of a 1s orbital. So next in our filling pattern comes 2s, then 2p, and remember that there are 3 of those, the 2p's, right? So they correspond to these different m sub l values of -1, 0, and +1. So I'm going to put those labels down there. So 1s, 2s, 2p. Next would come 3s, like this. Very good. And we can stop there. So let's look at an oxygen atom. So how many electrons does an oxygen atom have? So looking on the periodic table, we see that an oxygen atom has 8 protons, that's the atomic number, so it's going to have 8 electrons in the neutral atom as well, because we have to balance out the protons in the nucleus. So we've got 8 electrons to assign to orbitals. So we're going to follow first our 3 rules, right? Aufbau, Pauli, and Hund. Okay, so Aufbau says we're going to fill from low energy to high energy, so we start at the bottom of the ladder. So I'm going to draw little arrows to represent, I'm going to draw a half arrow like this to represent spin up, and that's an m sub s value of +1/2. And then I'll draw a little half down arrow that looks like this to represent spin down. And that'll be an m sub s value of minus 1/2. So let's do that. So here we put one electron in the 1s, so that's filling from bottom to top. Now the next electron, where can I put it? Well, it looks like I can still put another one in here, so if I put another electron like this, okay, now I've got a problem. So does anybody see what I've done? Whose rule have I violated? Ding, ding, ding. That's right. If you said Pauli, you were correct. So Pauli says that no two electrons in the same atom can have the same set of 4 quantum numbers. So let's go ahead and write down the 4 quantum numbers that this electron that I'm pointing to with this arrow has. So it's in the n equals 1 shells. So the n quantum number is going to be 1. The L quantum number can only be, well, it's an s orbital, so s, remember our code, means L equals 0. And m sub L, so since we're in an L equals 0 orbital, the only m sub L value is also 0. And what is the m sub s value of this electron that I've placed down? Plus 1/2. So this other electron that I've put in here has exactly the same set of 4 quantum numbers, and Pauli says you can't do that. Alright, so that electron is gone. So what can we do? Well, we could put another electron up here, but in fact we can stick another electron down in the 1s, just pointing with a different spin. So now its first 3 quantum numbers will be the same, 1, 0, 0, but its m sub s quantum number will be minus 1/2. Once we've done this, once we've got one spin up and one spin down, this orbital is now full. So that is all the electrons that it can hold, because if I put another one in there, I'm going to violate the Pauli principle. And experimental evidence says that you don't want to do that. So we're not going to do that. So 2 electrons only, 1 spin up, 1 spin down. So that's 2 of our 8 electrons. So where does the next one go? Well, the next place in energy, right? So the 2s. So we're going to put 1 electron there, spin up. The next one can go in that same box, spin down, and now it's full. We can't hold any more in that orbital. So where does the next electron go? We go up in energy to the 2p. Now I've got 3 orbitals, minus 1, 0, and plus 1, that might correspond to, you remember, the px, the py, and the pz, that differ in their orientation in space, but they all have that kind of dumbbell shape, right? So which box should I put it in? Well, in fact, it doesn't matter, because they all have the same energy, so I could start wherever I want. I'm just going to start over here, but that's completely arbitrary. It doesn't matter. All right, and I'm going to put this electron spin up, but again, it doesn't matter. I could have put it spin down, and that doesn't matter, but I'm going to put it spin up. Now the question is, where does the next electron go? Well, before I've been filling up these boxes, so you might be tempted to put another electron spin down in this first box. But who would tell you that you're not supposed to do that? That's right, Mr. Hund. So Hund says you want to maximize the parallel spins. So this atom will be slightly more stable if I can line up the spins like this. So the Hund's rules tells us that we want to line up our spins so that certain magnetic properties of the atom kind of reinforce each other. You could think of it like that. So we're going to put our next electron there. So how many electrons have we placed down? 1, 2, 3, 4, 5, 6. So where does our 7th electron go? Right here. We're going to maximize our parallel spins. So now we've got 3 parallel spins. They're all spin up. So where does the 8th and final electron go? Well, it doesn't go in the 3s because we still have space down here in the 2p, so we want to follow the Aufbau Principle. So start low if you can. So it could go in any one of these boxes, but it has to go spin down. So again, arbitrarily, I'm just going to put it in this first box. So I'm going to put that electron spin down in that first box. And that would be the electron configuration of oxygen. Okay, so it corresponds with what we've seen from photoelectron spectroscopy as well. 1s2, 2s2, 2p. Now we've got 1, 2, 3, 4, right? 2p4. So that would be the correct electron configuration for oxygen. The n equal 2 shell is the valence shell, so oxygen has 6 valence electrons, like we've talked about before. But you'll notice that this orbital approximation gives us some more information about those electrons. In particular, it tells us that we have 2 unpaired electrons. And so those spinning electrons are going to generate little magnetic moments. And so an oxygen atom is going to be deflected if we pass it through a Stern-Gerlach experiment. So it is a paramagnetic atom. And so that's a prediction that we can make from this theoretical model that we could not have made from our earlier shell model. So this has given us a little bit more information in thinking about what the spins on the electrons are doing. So this quantum mechanical model with spin added in after the fact is gives us a little bit more detail. Okay, so that's how we do that. Another thing that you should be able to do is for any electron that is shown on one of these energy level diagrams, you should be able to identify the set of 4 quantum numbers associated with that electron. So we did that down here, but let's pick another one to do it with. So let's pick this electron like right here that's in this box. So because I've labeled the m sub l values down here, it's going to have a particular m sub l value. So let's list the 4 quantum numbers associated with that electron. So the n quantum number is going to be 2 because it's in the n equal 2 shell. That's what this first number here on 2p tells you. And then since it's a p, p is telling you that L is equal to 1. That's our code. So L is equal to 1 for all p-type orbitals. Next we have the m sub L value, and again I've picked an electron that I have labeled in my +1 box. Now you can label these boxes any way you want, in any order. Anyone could be -1, +1, or 0. I just picked this order. But once you have them labeled, you want to pick the consistent quantum number with that label. And so this box, this electron, is in this +1 orbital. This little line right here is representing the +1 orbital. So I'm going to say m sub L equals +1. And that will correspond to one of those p orbitals that we've talked about, px, py, or pz. And it's not important which goes with which. And finally our m sub s value, since this is spin up, we're going to call it +1/2. So that would be the set of 4 quantum numbers associated with that electron. A way to think about these quantum numbers then is it's kind of like a seat assignment at a sports stadium, right? So you have to go to the right section, and then within that section, it might be divided up into rows, and then finally you have your seat number. So you have to find all those things to find your seat. Similarly, an electron has a certain assignment of quantum numbers, and that tells you which orbital it's going to be in and what spin it's going to have. So as we've already talked about, these orbitals relate to organization of the periodic table. And we can go in and fill out one of these diagrams for any atom on a periodic table. And so in this case, we want to write the ground state electron configuration for the element francium, also sometimes pronounced francium. All right, and it has Z, the atomic number of 87. So it has 87 protons in its nucleus. So we want to look at the periodic table and be able to write down its electron configuration. Now we could go through the trouble of drawing one of these energy level diagrams for the whole francium atom. That would take a long time, so we're just going to be interested in the electron configuration. So some people have asked, well, why is electron configuration important? Well, it turns out that electron configuration is really what it's all about in terms of making the behavior of one atom different from the behavior of another atom. So we've already seen that we can explain things like radius and ionization energy with our shell model, and electron configuration is related to that. We will also discover that electron configuration has a lot to do with the kind of ions that atoms will form and with the kind of reactions that those atoms can undergo. So for example, atoms with a valence electron with a low ionization energy that's very far away from a very small core charge, well, that electron is going to be easy to remove. So in reactions that involve taking an electron away, well, that substance is going to react very well because it's really easy to remove an electron from that kind of atom. So electron configuration is really important in helping us understand and think about why aluminum atoms behave very differently from carbon atoms, even though they're fairly close together on the periodic table. So what I'd like you to do is try to write down the electron configuration of francium using the periodic table trends that we've already seen, and then come back to pause this video, and then come back and we'll check the answer. So if you've paused the video, you're now ready to see the answer. So here's the answer for the electron configuration for francium. So remember, we start up with hydrogen, and we kind of count our way down until we get to the atomic number that we want. And because we know the filling pattern, we can fill each orbital with electrons until that particular orbital is completely filled. So remember, S's are filled when they have 2 electrons, and then we add 4 each time. So the P's are filled when they have 6, the D's are filled when they have 10, the F's are filled when they have 14. And then we will go to our next level. And so you just work your way across the periodic table until you get to the element of interest. So we would start here with hydrogen at 1s1, helium would be 1s2, and then we keep working our way down. We go through the P's, we get to 4s, remember we fill the 4s before the 3Ds, then we go across the first row of the transition metals until we get to zinc at 3d10, then we start with the 4Ps again, filling those, then we go to 5s, 4d10, and so on. After 6s, we jump down and start filling the Fs, so we jump down to those lanthanides, so that'll be 4f14, 5d10, 6p6, and then 7s1. So remember, francium, that element right there, is in the group 1, the first group of the periodic table, and so all the elements in that group have this S1 electron configuration. So if we want to, we can use shorthand notation for all this, and all this junk right here, all this stuff, wow, is the same electron configuration that the noble gas radon has. So radon is going to help us out a lot in this case because we can shorten our notation. It's bad if you happen to find it in your home because it can promote lung cancer and so forth, but in this case it's a real helper. So the same electron configuration as radon, that's what this notation means, plus this extra bit, 7s1.